Well, let me just so welcome again to this week's Origins Colloquium. It's a great pleasure to welcome Scott Tremaine, who received his PhD from Princeton in the mid-70s, was a professor at MIT, then back in Canada at University of Toronto as director of CETA, and professor and chair of the astrophysical sciences at Princeton, and now currently at the IAS in Princeton, famous for much work in dynamics in the solar system and in galaxies. So welcome, Scott. Please go.
Okay, thank you. I'd like to talk about two subjects today. One is what I'll call the standard model for the formation and orbit with the solar system comet cloud, and the second is applications of the standard model to try to understand one or at least of most of modern gravity. For the purposes of this talk, comets are simply pieces of ice and rock a few kilometers across. The images here are images of comets that have been received from close encounters with spacecraft. Comets believed to be leftover small bodies from the formation of the solar system, sometimes called planetesimals, and in the standard theory of planet formation, planetesimals collide and can coalesce and gradually build up the terrestrial planets in the cores of the giant planets. The comets become visible because there are volatiles in the surfaces of the comet nuclei, and those volatiles produce particularly thick atmosphere around the comet and a tail as they sway from the comet. That's what makes comets so specular and so visible when they come close to the sun. On the other hand, at large distances from the sun, there is no coma, there is no tail. Comets are visible only as a result of reflected sunlight in the nucleus. So the brightness of the comet falls off like a very high power the distance it's away from the sun. Consequence of that is that very few comets have been discovered beyond a few AU from the sun. The consequence is because they only become visible once they're losing volatiles. Once the comet does become visible and survive more than a few hundred orbits. A consequence of that is that since we believe that all the comets were formed early in the history of the solar system, there has to be some sort of cometary reservoir beyond a few astronomical units from the sun that both stable enough that it can hold the comets for the life of the solar system for a few gigayears, and yet leaky enough that it's continually producing a slow trickle of comets into the region where we can see them close to the Earth's sun distance. I'm going to be trying to deduce the origin of that reservoir from the properties of the cometary orbits. So this is just a quick review of the standard orbit elements in a potential. There's the semi-major axis and the eccentricity, the perihelion distance, which is a times 1 minus e, the closest approach to the sun. There's the inclination, which I'll always measure relative to the ecliptic, relative to the plane planets, and the orbital period. And Kepler's law says that the square of the orbital period in years is the cube of the semi-major axis in astronomical units. The energy per unit mass of the comet is minus g times the solar mass divided by twice the semi-major axis. But for simplicity, I'm going to set g to 1, solar mass to 1, 2 to 1, and minus 1 to 1. And so that I'll talk about 1 over the semi-major axis as being the energy. And for comparison, the Neptune major axis is the most known planet in the solar system is 30 AU, and Proxima Centauri is about 270,000 AU from the sun. So this is a plot of the orbital elements of the known comets. It shows the inclinational and the vertical axis in degree relative to the ecliptic, and the orbital period in years along the horizontal axis. Many comets that have extreme long orbital period, and rather than try to let them go off and then have them go off the end of the scale, here just taken everything with an orbital of 10 to the 5 years or longer and plotted it at an orbital period of the 5 years. The most prominent feature of this plot is this planet that's at relatively small inclinations at orbit periods of around 5 to 20 years. That clump doesn't extend out to higher inclinations. It doesn't end out to longer periods. So this clump has come to be called the short period comets. And the conclusion from this, since there's no dynamical mechanism that can take comets in isotropic distribution, squeeze to a flat distribution, the short period comets have to come a flat disk that's aligned with the planetary system. That was a prediction made in the 1980s, which was later verified with the discovery of the Kuiper belt. And this is just the discovery image of the first object in the Kuiper belt. We now know of thousands of objects in the Kuiper belt spread out around Neptune's semi-major axis at around 30 astronomical units out to about 50 astronomical units. And these are believed to be leftover planetesimals from the formation of the solar system. I'm not going to talk more about the Kuiper belt. Instead, I'm going to focus the more distant comets which have a larger orbital period and a roughly isotropic distribution of inclinations. Prototype of these is Halley's comet, which would be up here on the on this diagram. In order to use this diagram to understand the formation of these long period comets, it's better to make two modifications. The first is rather than using middle period, which goes like semi-major axis to the three halves, in order to focus more on the long period comets, it's better to use the energy or 1 over the semi-major axis as the horizontal coordinate. The second that's important to make is that the comets that we see have already passed the outer solar system, past Jupiter and Saturn, Uranus and Neptune. And in passing by those planets, they've received a kick to their orbital energy as a result of gravitational perturbations for giant planets. So in order to figure out where the comets have come from, it's better to plot what's called the original energy. That is, take the comet orbit, numerically extrapolate backwards outside the solar system, outside the planetary system, way, maybe 50 or 100 astronomical units. Ask what the semi-majors would have been out at those distances before the comet was perturbed the giant planets. When you do that, you get a lot looking like this one, the horizontal axis, the inverse semi-major axis. There's 1,000 astronomical units, 2,000, 10,000, and an inverse semi-major axis finally of 0, corresponding to a parabolic orbit. So in this plot, all the orbits to this side of 0 are bound. All the orbits this side of 0 are unbound. However, all of the unbound orbits, as far as we tell, probably unbound either because of observational errors in determining the semi-major axis or non-gravitational forces such as gassing. Therefore, the conclusion from this is that there's an enormous spike in the distribution of comet orbits, come to be called Oort spike, consisting of bound comet orbits with extremely large semi-major axes in the range 10,000 up to maybe 100,000 astronomical units. And the conclusion from that is that there must be a large reservoir of comets, the Oort cloud, which is bound to the solar system at distances of about 30,000 astronomical units from the sun. We can do more with this plot. We'd like to understand the distribution of these comets. And there's simple explanation for these, which is, as I said, every time a comet comes into the inner solar system, it experiences gravitational perturbations from the giant planets. So if you have a comet from the Oort cloud that comes into the planetary system, it comes close enough to within a few astronomical units so that we can see it, it'll get a kick in its energy inverse semi-major axis. The size of the typical kick is about -3 inverse astronomical units, which on this scale about this big. That every comet after its first passage through the inner solar system has a 50% chance of getting kicked onto escape orbit, will leave and we'll see it again. The 50% chance of getting kicked onto a somewhat more tightly orbit somewhere in this vicinity. If the comet is kicked onto a bound orbit, it'll come back again and it'll get a random kick, and it'll random walk in energy either until it goes to a much more tightly bound energy, or until it goes to an ape energy, at which point it's lost and we don't see it in. Surviving action to escape for n orbits is been by the classical Gamma-Ruin problem, and goes like n to the -1/2. It modeled the Gamma-Ruin problem for comets. You can fit this distribution, but in order to fit it, you have to take account of that comets are steadily losing volatile material, and that as they lose more volatile material, they fade. Fraction that if you assume that the fraction that survives loss of volatiles for orbits goes like n -0.6, which is plausible but still empirical, then you can do an excellent job of fitting this distribution of comets down to much smaller semi-major axes. I just wanted to point out, although the statistics here involve a couple of hundred comets in the Oort cloud, Oort's original paper back from 1950 only had a dozen or so comets in the Oort cloud. So it's a reminder that in the days of modern times of big data, if you have the right idea, you can still get away with very small amount of data. You can say more of the distribution of the comets in the Oort cloud. The cloud is so large, 1/10 of the distance to Alpha Centauri, that the kicks from passing stars and torques from the galactic tide are sufficiently strong to randomize the orbits of stars in the Oort cloud. That means that the distribution of comets on the constant energy surface in phase space is ergodic. It's uniformly distributed on the constant energy surface, and that means in turn that the fraction of comets with a perihelion less than q goes like simply just the ratio of q to the semi-major axis when the perihelion distance is small. That's actually what you observe, that this is cumulative distribution of the number of comets as a function inside give perihelion distance. You can see that it follows this linear relation with q up until about 5 or 6 astronomical units, at which point it starts to fall off because of the difficulty of discovering comets. It's large perihelion distance. This also predicts distribution of comet in the Oort cloud is isotropic. It says that the distribution of comets with inclination less than some value of cosine inclination should go like 1 plus cosine inclination over 2. And that's, again, what you see accurately for the Oort cloud comets. You can do more with the estimate of the properties of these of Europe. We know that the rate of arrival of comets Oort cloud with a perihelion less than about 1 AU is about 1 per year. We know the orbital period at 30,000 AU in the middle of the Oort cloud is 5 megayears from Kepler's law. We know, as I've just said, that the fraction comets with with perihelion less than 2 goes twice q divided by the semi-major axis. That tells you the number of comets in the Oort cloud is simply the rate at which they go through perihelion times the orbital period times the fraction that you see, which is a 1 over 2q over a. So that's 1 per year. That's about 5 years. And this is 2 astronomical units divided by 30,000 gives you a total of about 1 times 10 of comets in the cloud. With a typical cometary mass, we get cometary sizes of a few times to the 16th grams. The total cloud mass comes out at of order in an Earth mass, maybe a few Earth masses. This estimate was made by Oort. It's worth stressing that this is an extrapolation from the number of comets that Oort actually saw, a factor of 10 to the 10th. But even with the elapse many decades, Oort's estimate is still believed correct within a factor of few. So this is perhaps most spectacularly successful large extrapolations been made in history of astronomy. So far, I haven't talked about formation of the cloud, but it's a simple model for how the Oort cloud was formed. This model starts once the giant planets were fully formed from planetesimals that later accumulated to form planetary cores, later accumulated gaseous envelopes. But the process of accumulation into the planets wasn't perfect. Were likely to be leftover test particles, planetesimals, on nearly circular, nearly coplanar orbits between the giant planets and outside Neptune. We believe that the giant planets migrated early in the history of the solar system, and we believe that Saturnus and Neptune migrate outwards. As they migrate outwards, they came closer to the planetesimals that were left over for formation of the solar system, and their gravitational encounters excited the eccentricities of the comets, causing the comets to random walk to larger eccentricities in semi-major axes. Eventually, kicks from passing stars in the galactic tide exerted enough of a torque on these very elongated orbits. The perihelion grows, and the perihelion grows enough so that they no longer come close to the giant planets. At that point, they're no longer getting kicks from giant planets. The orbital evolution slows dramatically. The comets join the Oort cloud. They continue, once they're in the Oort cloud, to undergo random walk as a result of kicks from passing stars. That random walk occasionally the comets back to perihelion distances with a few astronomical units or less, where the comets plunge into the inner solar system, visible and are added to a comet catalog. The nice thing about this model is that essentially in the model can be computed through large body calculations. And all you have to do is start with the giant planets passing some stars from the solar neighborhood, a selection of test particles, and follow them for 5 billion years to see what happens. Only empirical components, the fading mode. When you do this, results look like this. This shows the distribution surviving test particles after 5 billion years. This is the semi-major axis, and this is centricity and inclination relative to the ecliptic. This cloud of points here is the cloud. You can see that it starts with an edge of around 2,000 astronomical units and goes out at least 100,000 astronomical units. It's rough spherical and isotropic, as we observe once the comets, once you get beyond about 5,000 astronomical units. There's a track of comets are still in eccentricity orbits that cross Neptune's orbits. These are the ones that are still undergoing a random walk minute ticks from the gravitational field of Neptune. Number left is transiting sort of track of comet goes down rapidly with increasing time. The efficiency of this process is about 5%. Most of the original planetesimals are ejected from the solar system, but we now believe that about 5% original planetesimals that started this process are still present in the Oort cloud. So the natural question is whether this can produce the Oort spike that I showed earlier in the talk. The gray distribution here is the observational data of comets Oort spike. Again, focus centered between Pollock orbits inverse major axis of 0 and semi-major axis of about 30,000 astronomical units. And what I plotted on top of the gray histogram is the result from simulation. Since we don't know what the fading law is I put in different colors. Blue is new comets coming in for the first time. Green is comets who have come back 2 or 3 returns. And then the red is anywhere from 5 to 25 returns. You can see that if assume that the fading law eliminates comets after a handful of returns, you can get a very good agreement, essentially no free parameters in the theoretical distribution of comets coming into the inner solar system and the observed shape of the Oort spike. The Oort spike is a little lighter. That's simply because of observational errors and non-gravitational forces. It's a little lower because it's got the normalized to the same amount because it's wider. The peak is a little lower. So I think this is a real remarkable demonstration that the Oort spike can be produced from principles with essentially no parameters except for the fading model. Let me then move on to asking what this can tell us about modified gravity. As one of the paradigms of modern cosmology is that the universe contains 5 times as much dark matter as it does baryonic matter. I'm going to tout a theory of modified gravity called modified Newtonian dynamics, MOND, which replaces dark matter by a breakdown in Newtonian gravity. That would be Planck's equation. Or Newtonian dynamics, that would be the law of motion below a critical acceleration, which is about 10 to the minus 10 meters per second squared. MOND has been remarkably successful at explaining a wide variety of phenomena on galactic scales that I'll say a little more about in the next slides. And the way to think about MOND is that, first of all, in standard dark matter for an axisymmetric system like a disk galaxy, observed stars and gas give you a real acceleration, which I've written as G bar for baryonic. In standard cosmology, the actual acceleration that you see that you measure, say, with a galaxy rotation curve, is the baryonic acceleration plus the acceleration due to the dark matter. In contrast, in MOND, there is no dark matter. The actual acceleration is given by nonlinear function, the baryonic acceleration, defined by transition function called mu, that approaches unity for an argument for accelerations much bigger than a naught. That's good because we know that Newton's law works very well when the accelerations are large and approaches the argument that is G over A naught when the accelerations are very small. The first thing you can see that this predict the observed acceleration should be a unique function of baryonic acceleration independent of the properties of the galaxy. And that's what's plotted here. This is observed acceleration This is the baryonic acceleration for a large sample of galaxies. And you can see that remarkably over two orders of magnitude, the observed acceleration is a nonlinear but universal function of the baryonic acceleration. Deviation of only about 1.1 or 0.15 dex over a range of 2 orders of magnitude. So that the proponents of MOND argue that this is something that's predicted by simple model dark matter and is predicted successfully by MOND. The second prediction is that if the acceleration is small, then the transition function mu goes x. So the observed acceleration could go show like the square root of the baryonic acceleration. At large distances from a isolated system, the baryonic acceleration should go like 8 times the total mass divided by r squared. The acceleration is just the centripetal acceleration v squared over r. So you conclude that the circular speed in the galaxy should go the 1/4 power of the baryonic acceleration. This is a plot baryonic acceleration for a large sample of galaxies as a function of the asymptotic speed. The dashed line is m goes like v to the fourth. You can see that the prediction is satisfied extremely well over about 4 orders of magnitude. And finally, MOND predicted in detail the behavior of the rotator of the galaxy. This is again plots of the observed rotation curves of a couple of galaxies. The prediction MOND. The MOND predictions have one free parameter, which is basically the stellar mass ratio. And in these cases, can do an excellent job of fitting the rotation curve. So far, I've only described an accurate version of MOND that's valid for disk galaxies. The more general form starts with noting that Poisson's equation can be from a Lagrange involves the density, the gravitational potential. If you want to retain the idea that there's a slope potential, the most general modification Lagrangian that you can make is to replace the grad phi squared with nonlinear function grad phi squared. And when you do this and evaluate the Lagrangian, you find this leads to a modified Poisson's equation, which is provides the simplest and relativist version of MOND. So this is a flavor of MOND in which the modifications to gravity arise from the Poisson equation. Why is this relevant? Because in the typical distance of the Oort cloud at 30,000 astronomical units, the acceleration is only about 5% of the non-critical acceleration. That's that the behavior of the Oort cloud is a strong function of the of modified gravity rather than Newtonian gravity. It means since we have a successful theory of the Oort cloud using Newtonian gravity, all we have to do is take a numerical simulation of the standard model of the Oort cloud and replace Newtonian gravity with Mondian gravity or with a Mondian solution of Poisson's equation. And then do the same calculations we did before, in particular, reproduce the calculation we did before of the Oort spike, which you recall fit the observational data very well. See what a fit is like in MOND. And this is what the result looks like on the right-hand side. This is the Newtonian fit to MOND. This is the Newtonian fit to the properties of the Oort spike. This is the Mondian fit properties of the Oort spike. And you can see that it doesn't work at all. In particular, the observed Oort spike is much narrower than you get MOND. There's a modest peak due to the MOND was somewhat displaced from the actual in the Oort state. But tail of the Oort spike, no matter what you choose for the fading law, is far more prominent than you actually observe in the real solar system. So the conclusion from this is that MOND-based simulations can't produce the orbital distribution of the distant comet. This result is quite robust. It's robust to changes in the migration history of the planets or the migration history of the sun and the galaxy, and to a whole set of other changes that we tried experimenting with in the simulations. Our conclusion was that if MOND is the right theory of gravity, the simplest version of it involving the Bekenstein-Milgram-Lagrangian can be correct. There are other more elaborate formations of the of MOND, including relativistically covariant oscillations. But the problem is that all of these other formulations either have too many parameters to test. So, for example, there's a version called tripotent MOND, which involves three free potentials have to try to fit to the observed mass distribution. So most of them either have too many free potentials, two parameters that or simply don't generate well-defined equation motion. So the basic conclusion is that the comments tell us that it's the simplest version can't be correct. We'd be happy that it's more complicated versions of MOND if somebody can give us a unique and well-defined model, but so far nobody has done that. Almost there. Thank you.
Thank you very much, Scott. So we have about 20 minutes for questions.
Maybe you're still mute, Jonathan.
Well, I'm not muted, but can you turn your volume up, Scott?
No, I can't.
Can
So
you
I
hear
can't
me?
hear you. Maybe we should. I should let me leave the Zoom and I'll come back in.
Yes. So then people can be thinking of their questions for the discussion. Can you hear us now, Scott? So, yes, Scott, if you perhaps rejoin if you can. So, Scott, can you hear us now?
Okay, try again. I can hear you.
Can you hear us?
Nope.
Do you want to try leaving and joining? I'm not muted now, but let's see if you can do here. Maybe we can. Let me see if I can remove you. Maybe no, maybe I should not. Scott, do you want to try leaving and rejoining? Okay, that's what he's doing. Okay, hello, Scott. Can you hear us?
Yes, I can hear you.
Great. Great, then let's start with some questions then. So perhaps for the model of the Oort cloud, do you have a need for a capture term, so capturing extraterrestrial comets?
Or do I have a need for
A model of a term for capturing comets? Is that necessary in the model, or can you place some constraint on it?
It's not needed in the model. It's particular issue early in the history of the solar system when the sun made a part birth cluster, and where there could have been exchange of comets between different stars in the birth cluster. In the current solar environment, the flux is small enough that it's a negligible change to the evolution of the cloud.
Okay. We recently had a talk with Bob Lowe. I'm glad to see here actually, where there was some estimates of recent comets have come in uh, purported to be extrasolar in origin. Do you have a view on that and the current rates of extrasolar comets?
There are certainly there's certainly we've discovered two extrasolar comets, or at least extrasolar bodies look somewhat like comets. The flux of those is obviously non-negligible. It's and watching out for is going to be an extremely interesting activity over the next few years. However, the system is inefficient at capturing them, in the sense that they come in on strongly hyperbolic orbits. It's rare that they would come close enough to any of the solar system planets that they could be converted from hyperbolic to elliptical orbits. And so in the vast majority of cases, they'll come in, go through the solar system, and go out again.
Mm-hmm. So people should raise their hands in Zoom or jump in if they have a question or comment. But we've discovered two solar comets coming in within the 1 AU in the last, is it 10 years or so, and the rate 20% the normal influx.
Yeah, we've heard two in the last 10 years. The rate is very uncertain, not just because there have only been two, but because the properties of the two are grossly different. One, which is Comet Borisov, appears to be fairly normal. A comet might easily have been ejected from a neighboring solar system. The other, Oumuamua, is much smaller and didn't exhibit any evidence of an atmosphere or a coma. That Oumuamua was much difficult to discover. And so it's a little difficult to understand why we've discovered one from a population that's really easy to discover, and the other from a population that's quite difficult to discover.
Okay, great. Let me see. You mentioned Planet 9 right at the end.
I'm afraid I've lost lost you again. Let me
Okay, Scott, can you hear us again?
Yes.
Great. My next question was about Planet 9 and its impact in the model of the evolution of the outer comets. Do you you obviously don't need it, I guess, in your fiducial model, but can you constrain it?
Indirectly, adding the Comet 9, Planet 9 would not have any effect on the standard model for the formation of the Oort cloud I described. The reason is that the evolution is dominated by planets like Uranus and Neptune, and Planet 9 is much less massive and therefore has less influence on the evolution of the comets. It does indirectly have some influence. First of all, the arguments for Planet 9 are in part based on asymmetries in the distribution of distant Kuiper belt objects. So in that sense, the FPS for Planet 9 comes indirectly from the distribution of comets. And there's a set of comets. The standard model that I put forward says that all the comets came from the original protoplanetary disk, and have evolved as a result of the evolution caused by the gravitational perturbation giant planets. There are a small number of Kuiper belt objects called the detached disk. Those orbits don't come to any of the giant planets. It is difficult to understand how they got into their current orbits unless it was early in the history of the solar system birth cluster, or as a result of gravitational torques from an undiscovered planet.
Kedron, did you have a question that you wanted to?
Yeah. So am I understanding correctly then the standard version of MOND, the gravitational force is a bit stronger than normal at very long distances?
Yes, that's correct.
So then shouldn't this produce a population of apparently hyperbolic comets because the gravitational potential is then a little bit deeper?
Yes, that's correct. So it was my original view of what would happen when we did calculation is that you would get an Oort cloud that had a population of apparently hyperbolic comets caused by MOND. This actual situation is somewhat more subtle than that. The reason is that the solar system is embedded in the galaxy, and as because of its circular orbit in the galaxy, the solar system is subject to an acceleration, which is something called the external field effect in MOND, which changes the behavior of MOND, of the gravitational potential at large distances. So the main effect of MOND is not so much that the gravitational force is stronger at large distances, but it's not starkly symmetric at large distances, and that causes a flux of new comets to appear in at some major axes where you wouldn't see it in a standard Newtonian model.
Mm-hmm. Okay, thank you.
Great. Julia, would you like to?
I'm afraid I've lost you again. I'll come back in a second.
Okay. So maybe Julia next, and then Devesh when Scott returns.
Thank you.
Okay, Scott, can you hear us?
Yes, I can.
Okay, next question, please.
Hi, Scott. I'm wondering about the size distribution of the Oort cloud comets. Can you tell me something about it?
Yes, it's not very well known. It's not very well known because there's a limited population, and when you see the Oort cloud comets, the nucleus is obscured by the optically thick coma, and the optically and so you when you observe a comet, you're seeing an object that's bigger than the actual nucleus. I get the power law index, the size distribution, but the size distribution is such that most of the mass is in the largest bodies.
Mm-hmm.
Oh, thank you. And I have another question. I'm sorry. Is there comets in the inner Oort cloud the same size distribution with the outer Oort cloud? Are they the same or?
According to the standard model, it would be the same, but we don't know. The problem with the inner cloud is that we it's very difficult to detect comets from the inner cloud. We'll do better when the telescope is operating and they conduct their SSD survey. They should detect a far larger number of comets, and part of that much larger sample should include comets from the inner cloud.
Mhm.
Thank you so much.
Great. Devesh, did you want to ask your question?
Hi, Professor Tremaine. I was just wondering about this MOND theory, and you said there are a couple of extensions of this theory, and one such that I'm very vaguely familiar with is the scale invariance theory, where people are now claiming that it has no adjustment parameter, and it's used to explain essentially everything that there's no need for dark matter, and like I was wondering if you had a time to look into that, and what do you think of this no adjustment parameter claim they're making?
Um, well, first of all, let me make it. So the answer is no. I hadn't heard of the scale invariant theory. Who should I look up to learn about this, or where should I look it up?
Yes, I also found it's Andre Medere who's been working on this. Yeah, from the Geneva side of things. So yeah.
Okay. So no, I haven't. My only excuse is that I tried to learn as little about MOND as possible for the purposes of this project. So I don't know much about the alternatives to MOND.
Well, then maybe I mean, my recollection, what do the MOND folks say about the bullet cluster, for example, which was always claimed to be very direct evidence of dark matter?
Well, my own concern about the bullet cluster is that as technology improves, you get larger and larger samples. It seems to me to be more and more dangerous to look through a sample of thousands and thousands of galaxy clusters, find one that doesn't agree with a particular theory, and then say, this one doesn't agree with theory, and therefore the theory is incorrect. There are certainly other cases of clusters of galaxies. So the reason the bullet cluster is claimed not to agree with MOND, if I've gotten it straight, is that the gravitational lensing measurements show the mass is let's remind me of what's going on in the bullet cluster. It's well, let me not go into that for there are other examples of colliding clusters that don't standard cold dark matter all that well. And as I say, I think it's dangerous for any theory to look at a sample of thousands of objects, pick one of them, and then say this is inconsistent with
Sure.
theory.
Very good then. Now I had another question about the back
Sorry,
to
I'm gonna have to log out and log in again.
okay. Hello, Scott. So can you hear us again?
Yes.
Great. So I think maybe the last question then, but I wanted to clear up in my mind this evolution of the Oort cloud and the production of the Oort spike. So they're comets are getting kicked out from the inner solar system and then getting random kicks. So why should they pile up in this very low energy state, just very weakly bound? What can you remind me why they should pile up there and just explain
Right.
it?
So So they're getting this series of kicks from the giant planets, in particular from Neptune. They're gradually random walking at larger semi-major axes, and there comes a point at which the diffusion time scale for the random walk in semi-major axis due to planetary perturbations becomes longer than the torquing time scale from the galactic tide, and that only occurs when the major axis is quite large. When the major axis is large enough, the torquing time is sufficiently small that the comets acquire enough momentum to raise their perihelion distance enough so they no longer come close to Neptune.
Mm-hmm.
At that point, the kicks from Neptune are frozen out, and the comets become frozen in semi-major acts in the Oort cloud. They can continue to evolve in angular momentum, but the semi-major axis is physically frozen.
So what do we learn about the position of the Oort spike? Does it depend on Neptune's properties, or?
It mostly depends on Neptune's properties and to some extent on Uranus's properties. So one of the things to keep in mind is that people deal with comets usually make the assumption, for example, if you're looking at extrasolar comets, that all of the extrasolar clouds look like the Oort cloud, but in fact, the properties of the Oort cloud are a strong function of the details of the configuration of the planets and other stars that have different clouds.
Well, that's great to clarify then. Very good then. Well, thanks again, Scott, for a very nice talk and discussion. I'm sorry I had a few audio issues, but I think I certainly learned a great deal about this subject. So thank you again.
Okay. Thank you, and my apologies for the audio issues on my side. I don't know what